So chapters 13 and 14 are all about acids and bases. But for chapter 13, we're just going to focus on the nature of acids and bases. We're going to look more at equilibrium on chapter 14. And before I move on, there's this cool video that you can watch at your own convenience. I wouldn't have wanted this in class, but given extraordinary conditions, we cannot. So the link is below here. And oops, never mind. All right. So when we talk about acid-base reactions, or when we talk, I guess, about reactions in general, so we have a lot of subatomic species involved. It can be protons, electrons, or neutrons. For most cases, they're usually electrons, especially for organic chemistry, and in general for redox reactions. But for acid-base reactions, we're going to look at protons, how they're transferred from one species to another. We're not going to have time this semester to look at neutrons, but that's basically the heart of nuclear reactions, which is in chapter 19 if you want to do further reading. So acids and bases, they're all around, I guess, everywhere. You have a lot of acids from fruits. Let's say, for example, some citric acid is present in some fruits. You have bases in cleaning products. Let's say, for example, when you have Windex at home that actually contains ammonia, and so on and so forth. So it's actually important to study acids and bases to understand some natural phenomena. Now, when chemists define acids and bases, there's actually three definitions that they go by. So the Arrhenius definition, which is what you have learned when you were in high school most likely, and I think that's what we have looked at to last semester. So in an Arrhenius acid, you have a species which is donating an H plus in solution. Okay, and I have to stress it has to be in an aqueous solution. Okay, so for example, that will be hydrochloric acid, or any fans here of Breaking Bad, hydrofluoric acid. And then a species which donates hydroxide ions in aqueous solutions, again, are bases. Okay, so we have cesium hydroxide, potassium hydroxide, and then some common antacids like magnesium hydroxide and calcium hydroxide. Now, what we want to focus on for this chapter is this, the Bronsted-Lowry definition. Okay, Bronsted-Lowry definition is slightly different from the Arrhenius definition in the sense that the Arrhenius definition is actually just limited to aqueous solutions. For Bronsted-Lowry, it's a little bit more general in a sense that acids are defined as proton donors. Okay, and protons from here on forward, we're going to refer to them as H+. So just remember that when we were looking before at mass numbers, atomic numbers, and counting subatomic species, so if this is the notation for hydrogen, remember again that this means that hydrogen has a total of one proton, or rather, this is the mass number, which actually tells you the number of protons plus neutrons. Okay, just remember that. And then this one tells you actually the number of protons. So from here, you can actually see that hydrogen has no neutrons, at least this this isotope. Okay, so if we actually put here a plus charge around hydrogen, okay, so right now, if hydrogen has no charge, then to make hydrogen neutral, you have one electron. But if you take away that electron, then it's only the proton which is left. Okay, that's what it means by H+. So that's why it's called a proton most of the time. So get yourself convenient with that term. Alright, so that's an acid, meaning hydrochloric acid, which is HCl in liquid solution or in aqueous solution, and hydrogen chloride as a gas are both acids in this manner. And then you have Bronsted-Lowry bases, which accept those protons from acids, from Bronsted-Lowry acids. And for example, you have ammonia, So you can see ammonia is not an arrhenius base because it doesn't have an OH. And then you have methylamine. Again, shout out to my fellow Breaking Bad fans there. And then the most generic definition, which you'll probably use in organic, and we'll touch base of this, not pun not intended, in case you did not get the pun. No, never mind. Will be the Lewis definition. So for the Lewis definition, an acid is an electron pair acceptor, okay, versus a Lewis base is an electron pair donor. Okay, like for example, ions such as iron 3 plus. As you can see, they don't even have any proton to give to, but they can actually accept lone pairs. And all Lewis acids are Bronsted-Lowry all arrhenius acids and all Bronsted-Lowry acids are all Lewis acids, but not the other way around. Same goes with bases. Okay, in terms of reactions, because that's what chemistry is for. So in the arrhenius concept, or I guess in both arrhenius and Bronsted-Lowry concepts, acids and bases form a salt. Okay, so again, when an acid reacts with a base, you form a salt. Okay, we're going to look at whether that salt is neutral, acidic, or basic in this chapter. But so you can see, the first equation is just the reaction of hydrochloric acid with sodium hydroxide. The salt here is sodium chloride. And then for the second one, you have hydrochloric acid and ammonia. You form ammonium chloride. All right. Now, again, we're going to focus on Bronsted-Lowry bases and acids for this chapter. So there are a lot of Bronsted-Lowry acids. It's more generic, again, than the arrhenius definition because the arrhenius definition is limited only to aqueous solutions. So you can have, for example, some molecular compounds such as nitric acid. Okay, nitric acid, for example, when reacting with water as a base, okay, will give up this proton to yield the nitrate ion plus H3O plus. We're going to discuss what H3O plus is. You also have cation ions. So, for example, the ammonium ion can react with water to give up this proton, okay? And in that reaction, water is the base, and NH4 plus ammonium produces ammonia, and water produces H3O plus. And you can also have anions. Let's say, for example, this is H2PO4 minus. I forgot how to name this one. It can give up one of these protons, okay? It actually has 2 protons available. It's a diprotic acid. We're gonna look at diprotic acids next time. You can give up one of these protons, let's say, for example, that, or, well, according to the cartoon, the other one, to a base, such as water, and to produce HPO4 2 minus and H3O plus. Now, the same goes with bases. So bases are actually going to react with acids too. Here, water is actually behaving like an acid. Okay. Now, when water behaves like an acid in the presence of ammonia, it actually gives up a proton to ammonia to produce the ammonium ion, and water being deprotonated is left behind with just the hydroxide ion. Okay, then you have anions. Let's say, for example, the carbonate anion can also accept a proton from water, again acting as an acid to form the bicarbonate ion, which is shown here with this acid or with this proton. Okay, so H3O plus. So at this point, I'd like you to get comfortable and with the term H3O plus. We will be using H3O plus a lot. And H3O plus, as you can see, is just water. Okay, like for example, consider this first reaction. Let's erase everything. Okay, so this water, when it behaves like a base and accepts this proton, so you can see that it's as if it's just proton with the water. Okay, so H plus, H plus H3O plus. Okay, so that's just H plus. It's just like H plus H2O. Okay, so this is actually H3O plus. It's just hydrated proton. Okay, so hydrated proton, that's what H3O plus is. Okay, and because of this, chemists, and we will actually in class 2, use H plus and H3O plus interchangeably. Okay, so again, H plus is equal to H3O plus. Now, earlier, one thing I'm not sure if you actually noticed, but this reaction with ammonium and water actually produces ammonia. Okay, and ammonia is actually a base. But in the previous reaction here, ammonia, which again still behaves like a base, produces ammonium. So there must actually be a relationship between ammonia and ammonia. And in a chemical reaction, that's actually what conjugate pairs are. So a conjugate acid is the species formed when a proton is transferred to the base. Okay, so for example, if you have the bicarbonate ion HCO3 minus, its conjugate acid is carbonic acid. Okay, again, a base will have a conjugate acid, and in a similar vein, if you have a conjugate acid, you will have a conjugate base. Okay, so for example, here water behaves when it gives up a proton, you will only have OH minus, and you know that that's a base because you can actually, or this species rather, can take in a proton to reform water. The same thing with carbonic acid. It can give up that proton that it has just received when it was the bicarbonate ion to reform, well, the bicarbonate ion. Okay, so it's important to distinguish conjugate acids and bases at this point. Here are some examples. I'm not going to go over them, but I think you should be at least familiar with this to convince yourself how acid-base conjugate pairs are formed. Okay, now there are some cool species which actually act both as an acid and as a base. You have, for example, H2PO4 minus here when it reacts with a proton with water as a base. Okay, it produces a proton. Okay, so basically here what happens is well, a hydrated proton for that matter. What happens here is this species gives up a proton to produce hydronium. Okay, that's actually what that species is called, hydronium ion, and in effect gives HPO42 minus. And remember that this HPO42 minus is now the conjugate base. Okay. Now, on the other hand, when H2PO4 minus also reacts with water, but with water acting as an acid, okay, with water acting as an acid, water can actually give one proton to H2PO4 minus to form phosphoric acid, which is now here the conjugate acid of HPO4 minus, okay, leaving water with just a hydroxide ion. Okay, here's some list of polyprotic acids and bases. Again, we're not going to discuss them until later, but most of the polyprotic acids are actually the ones which are amphoteric. Okay, again, amphoteric species just behave or just act either as an acid or as a base. They can do both. So water is one of them. Okay, we have illustrated that in many examples already. Now, one thing that we want to actually look at for acids and bases is to determine the concentration of protons. Okay, where chemists are interested in determining the concentration of protons when you're working with an acid and a base. So, the autoionization of water is just a reaction in which water reacts with itself. Okay, there's only one known molecule which can do autoionization. It's water. Okay, so if we have water, okay, reacting with itself, this one water molecule, okay, can behave like a base. Okay, it can behave like a base. And this other water molecule, sorry, can behave like an acid. Okay, and when that happens, this acidic water will actually give up this proton to this basic water. Okay, and in effect, this water molecule number 1 will actually form this conjugate base, or conjugate acid, sorry. So the conjugate acid here is the hydronium ion, and the acidic water will lose an not lose an electron, but lose a proton, and again be converted into the conjugate base hydroxide. Conjugate base. Okay, if we write an equilibrium expression for that, remember that when writing equilibrium expressions, we don't include liquids and solids, okay, in the equilibrium constant expression. So the equilibrium constant expression is just K is equal to the concentration of hydronium ions times the concentration of hydroxide ions, okay? And we're going to call that constant Kw, the equilibrium constant Kw. Now, Kw, interestingly, has a value of 1 times 10 to the 14 at room temperature. And I said interestingly because this is actually the most powerful equation for chapters 13 and 14. In fact, this is the cornerstone equation for acid-base equilibria. Okay, Kw is called the ion product constant, again, for the self-auto-ionization of water. And in a neutral solution, the concentration of hydronium and hydroxide are equal to each other. By the way, again, this expression can be rewritten as also this, because H plus and H3O plus are just the same species. Okay. If you have an acidic solution, then that means that the concentration of protons is much greater than the concentration of hydroxide. Okay, self-explanatory. And in the basic solution, you have a greater concentration of hydroxide over hydronium. Now, Kw, like any other equilibrium constant, will change as a function of temperature. So for most of the time, we're going to actually work with Kw at room temperature. But just in case you're wondering, here are some values. Okay. Now, when working with acids and bases, we need to talk about their relative strengths. Okay. At this point, we're almost at the tail end of this video. I would like you to make sure that you know what the 7 strong acids are. Okay, we've discussed this already before. And there are 8 strong bases. All of them actually have OHs in them. Meaning, all of these are actually not only Bronsted-Lowry bases, but they're also Arrhenius bases. Okay, but just to give you a recap, what makes an acid strong is that it is a strong electrolyte. The same goes with a strong base. Okay, so a strong electrolyte completely, again, the word is completely. So completely dissociates into ions in solution. Okay, so for example, the strong acid sodium hydroxide will dissociate completely in solution as sodium ions and hydroxide excuse me, ions. And then you have sulfuric acid, which will dissolve completely or dissociate completely into H plus and SO4 minus. Okay, again, the word is dissociate, and for strong acids, that's complete. Okay, now for a weak electrolyte, there are only a few which dissociate in solution. Let's say, for example, formic acid. This is the structure of formic acid. So you can see when it reacts with water, or when it is in an aqueous solution, you actually only have a few hydronium and formate ions produced. By the way, I would like to just emphasize that another way to write this equation will be this. HCOOH, okay, equal to H plus HCOO minus. Okay, I'd like to just say that because some textbooks, including your own, actually prefer to write it this way. As you can see, this is different from this equation in the sense that we're not considering water as a reagent, okay? And we're only looking at the proton as a proton, not a hydrated species. But again, they're just the same, okay? Because this one anyway is also an aqueous solution. Okay, and then you also have ammonia. Ammonia is also a weak electrolyte. So here, remember that if this were the case, then the K values are actually very low, okay, because you only have a few products. Then you have non-electrolytes. There are no acids and bases which are non-electrolytes, but just an FYI. Or well, there are a few which are non-electrolytes, such as, for example, there's some degree of acidity with ethanol. But we're not going to discuss that in this course. That's for organic chemistry. Okay, so basically a strong acid, again, completely dissociates. Okay, a weak acid, slightly dissociates only. Okay, that means that strong acids will actually give up their electrons more easily than weaker acids. Okay, and then bases will hold on to protons more strongly than other bases. That's just what it means. And notice, by the way, here that as the acidic strength increases, let's say, for example, perchloric acid here is at the top of the pack. Its conjugate base, perchlorate ion, is actually the weakest base in this. Okay, whereas ammonia, the weakest acid, okay, I mean, I'm saying weakest acid even though it's a base, is actually, well, it will actually produce the strongest conjugate base in in this example. So there you go. As the acid strength increases, let's write that down. As acid strength increases, conjugate base strength goes down. And the same thing can be true as well for base strength. Okay, it's just that we don't have a table for that. As base strength increases, conjugate acid strength decreases.